day. Welcome again to today's class. Today we'll be discussing chemistry practical, WAEC base, determination of qualitative analysis of cations and anions. We decided to call it determination of qualitative analysis. We use the word qualitative analysis because in this analysis of cations and anions, what you are to say is whether it is present or not present, suspected or confirmed. So we are using the word present, suspected, confirmed, not present. We are not checking in what quantity do we have this cation in it. If we are checking the quantity, the cation present in a particular salt is, it means that we will change this topic to quantitative analysis of cations and anions. Okay, so in this video we want to focus on qualitative analysis. This is WAEC based because in WAEC they have cations that they love to ask on, and they have the anions they love to ask on. Then when you come to university setting or university level, there are cations and anions, and the number of them they will expect you to get. Okay, then we want to go into the cations in full. But before you go into analysis of cations or test for cations, it is important that you do your physical examination of that salt first. I repeat, check the physical examine that salt physically well first. Check the physical examination under the color, the odor, the texture, and solubility in water. How do you do it? First, color. I'll bring the salt. Let's say this is the salt. This salt is white. Instead of me to say the salt is white in color, the best word to use while trying to describe the color of the salt, which is white, is the salt is colorless. The salt is colorless means that it is white. Please, if you write the salt is white, they will mark it bad for you. It means you are not a scientist or a future scientist. Please, white salt, the best name to it is colorless salt. Then if the salt is not white, maybe green, blue, red, whatever, say that salt A is colored. Salt A is colored. Open a bracket and say green in bracket or blue in bracket. Then if the salt, as you are looking at it, is like green and it is also like brown, that is two different colors is what you are seeing, say that salt A is mixture of two salt. Under your observation, say that salt A, let's say now under the color, text color, my observation there is that salt A contains color, mixture of color salt, mixture of colored salt, and that would be my inference. Salt A, mixture of. Now under the inference, under the color, when you check it and it's having two color, maybe green and blue or green and brown, it means that you will note that the salt A contains mixture of colored salt. Your inference will be iron 2, comma, iron 3, comma, chromium this, comma. Just list some of the colored salts you know. Say suspected. Suspected. Then even when you have that it is only one color you are seeing, and you say under color test observation, the salt contains colored salt bracket green, salt A contains colored salt bracket green. Then the inference, you list some of the colored cations you know. Iron 2, iron 3, chromium 3, etc. Suspected. Whenever they see such inference, the implication is that you have succeeded to tell them that they are colored salt, or they are some of the colored salt we have. When you are done with your color, check for texture. That is, touch it with your what? Palm. Touch it with your what? Palm. Like this. Touch it like this, your finger. Then, if it is crystalline, you are checking texture under crystalline, granular, and powdery. If it is crystalline, how will you know? If you have touched sand that look as if it has teeth, or you perhaps go and touch sugar, the way sugar look like or feel on your finger, that is what how crystalline salt is. Then if it is powdery, normal powder, you know. If it is powdery, note it. Then if it is granular, note it. So salt is granular, salt is powdery, salt is crystalline. Then you come to what? Odor. Most time the odor of a particular salt is odorless. Most salts are odorless, but if you ask odor, specify the odor. Okay? Then we go for solubility in water. Solubility test. That solubility test is very helpful. With solubility test, it will help you to know if the salt contains mixture of soluble salt and insoluble salt. See how we do it. Get the salt sample, put little of it inside your what? Conical inside your test tube, please. Then take distilled water, just add water inside it, shake it very well. Heat the solution, heat it. As you are heating it, after heating it, check if the salt are very soluble. Once the salt is very soluble in water, once it is very soluble in water, it means that ammonium ion radical, sodium, potassium ion will be highly suspected. I repeat, ammonium ion radical, sodium, potassium ion will be highly what? Suspected. That will tell you that why you are suspecting these cations, ammonium ion radical, sodium, and potassium, is because they are very soluble in water. They are very soluble in water. Also, group 6 cations. Group 6 cations are very soluble in water, and that is why group 6 cations do not have precipitating reagents or agents. So, group 6 cations, ammonium ion radical, are very soluble in water. So, when you put it and it's very soluble in water, know that, go and look for tests for this to know which of this will be what in your salt. Okay? Then when after eating it is not very soluble in water, say that salt contains, once it's not insoluble in water, please pause. I know why I say please pause. Please pause. Okay? Come down to what? Test for cation. Pause. I will still tell you why I say pause. Come down to test for cations. You have left solubility test, you enter test for cations. Bring the small of the salt, add 2 drops of dilute sodium hydroxide solution into it. When you add it, if it forms a white PPT, it means that it does not have a what? Ammonium or sodium, or even it doesn't have ammonium or sodium what? Ion. Are you getting it? And it's also possible that it does not have soluble cations in it. It's also possible, but we will not generalize it, we will not confirm it then. Because I put 2 drops of dilute, this is giving me YPPT. That is when I will now go and say, and that's my observation, salt contains what? The inference, salt contains insoluble what? Salt likely contains insoluble cations. But if I add this and it didn't form YPPT, no precipitate is formed, and in that my solubility test that I have insoluble solution form after I have eaten it, the salt plus water plus it is still forming insoluble in that solubility test, and I did 2 drops of dilute NaOH solution and I'm getting no PPT. Wow. I heat it again, I moist my red litmus paper. As I'm heating it, I put my moist litmus paper and it's changing the moist red litmus paper to blue. Ammonium radical is confirmed, and ammonium radical is soluble in water. That means the inference I'm to write in that solubility in water where it is not soluble is that salt A contains mixture of soluble and insoluble salt. Are you getting it? Then I'm done with my solubility. You know, this is, you are using your experience as a scientist to analyze this. Then when it is YPPT, I am suspecting any of this. I will not say this is confirmed. I'm suspecting any of these cations. Then I'll say this happened with 2 drops of dilute NaOH, that is sodium hydroxide, that is pump. That is when I will be talking about YPPT. But when I now put excess of what? Sodium hydroxide, and the white precipitate remains. If the white precipitate remains, look at the cations I will be suspecting. But if the white precipitate disappear, look at the cations I am suspecting. That means that aluminium, zinc, and this forms white precipitate in drops of dilute NaOH, but the precipitate disappear in addition of excess NaOH. Then magnesium and barium form YPPT, white precipitate, in drops of what? Dilute NaOH, and the precipitate remains in excess what? Sodium hydroxide addition. Okay, now I've been able to reach to this stage. I will now say plus dilute H2SO4 solution. Why? I want to know whether magnesium and barium is present. When I put this and it's giving me colorless solution, that is the white precipitate disappear, forming colorless solution, it means magnesium will be suspected. But when I put dilute H2SO4 solution and precipitate remains, the white precipitate remains, barium will be what? Suspected. That means barium forms white precipitate in drops of dilute NaOH and in excess sodium hydroxide and in also dilute H2SO4 solution. Then we come to this. We have 3 cations to analyze plus 2. When you add this solution we have, which is excess sodium hydroxide with the salt, which precipitate disappear, when you add the 2 drops of ammonia solution, When you add 2 drops of ammonia solution, something will happen. What will happen is that white precipitate will form. When the white precipitate form, I say 2 drops of ammonia solution. When you see white precipitate, suspect 2 things: aluminium, lead, and what? Zinc. But when you put excess ammonia solution to it and white precipitate disappear, zinc will appear. Suspect zinc. That say that zinc is confirmed, because zinc is very soluble in what? Excess ammonia. But aluminium and lead are not soluble in excess ammonia. We are done with this. Recall that we said when we put excess NaOH, that's sodium hydroxide, if precipitate remains this. But if precipitate disappear, that is, no white precipitate is formed, that is, these are soluble in what? Excess sodium hydroxide. Once precipitate disappear, it means aluminum, zinc, and lead are soluble in excess sodium hydroxide solution. Question can come from here: which of the following cations are very soluble in excess sodium hydroxide solution? Look at the answer: aluminium, zinc, and lead. They are very soluble there. Now we want to separate them. We want to know which of them, how to determine each of them. Then we said plus 2 drops of ammonia solution. When you add 2 drops of ammonia solution, a white precipitate will be formed. Once the white precipitate is formed, it means that aluminium, lead, and zinc are still to be what? Suspected. When you add 2 drops of ammonia solution and you are still seeing this, it means that you will still suspect these 3. Because white precipitate forming means that these 3 are not soluble in drops of ammonia solution. Remember, in 2 drops of ammonia solution, this will still be suspected. But when you now put excess of what? Ammonia solution into that mixture, if you put excess, that you pour excess ammonia, what will happen is that only aluminum and lead will still have white precipitate. When you still have white precipitate, it means aluminum and lead is what you'll be suspecting. But when you did not see white precipitate again, that is, it disappeared, zinc is what you will be suspecting. Okay? Then another thing is you need to now see how to separate this. From this, we have realized that zinc is very soluble in ammonia. And we have also realized that aluminum, zinc, and lead are very soluble in excess sodium hydroxide solution, but insoluble in drops of sodium hydroxide solution. These are not soluble in drops of what? Excess drops of sodium hydroxide solution. Aluminum, zinc, and lead are not soluble in drops, but are very soluble in excess addition of sodium hydroxide solution. That is it. Then we also realize that zinc is soluble in ammonia. From this level we are. Zinc is soluble in ammonia, in excess addition of ammonia. Zinc is soluble in excess addition of ammonia. Aluminum and zinc and these are soluble in excess addition of sodium hydroxide. So we said aluminum, zinc, lead equals to soluble in excess sodium hydroxide solution, whereas zinc is soluble in excess ammonia. Please note that. You will see everything well explained here. When it is in 2 drops, they are not soluble, they form white precipitate. But when it is excess, they are very soluble. Soluble means that the white precipitate disappears. That is by the way. We'll come to this. When we put excess ammonia, zinc came out to show that it's soluble in ammonia because the white precipitate disappeared. But in this, the white precipitate remains. Aluminium and lead will be suspected. Then add dilute H2SO4 to separate aluminium and lead. You will add dilute H2SO4. You will notice that if it is colorless, that is white precipitate disappear. If it is colorless, aluminium will be suspected. But if white precipitate is formed, lead will be suspected. That means lead is insoluble in dilute H2SO4, but aluminium is soluble in dilute H2SO4. That is what it means. Then we'll come to this side. We said that when you carry the small salt and you add 2 drops of dilute sodium hydroxide solution and it gives you green precipitate, suspect iron 2. For you to be sure of iron 2, assuming you only have 2 drops of dilute NaOH and you want to confirm iron 2, what you do is that once it gives you green precipitate, leave it for some minutes. Leave it for some minutes to react with air. After minutes, if it changes to reddish brown or brownish precipitate, it means what? It has oxidized to a what? Iron 3. Iron 3, that means iron 2 is what should be in that salt. But if you still have other reagents like potassium thiocyanate, what you do is that when you add 2 drops of dilute NaOH, that means you must have orange precipitate before you say iron 3, not iron 2. If you have orange precipitate, you say iron 3. Then to confirm that it is iron 3, add your 2 drops of potassium thiocyanate. If it gives you dark red solution, it means it confirms iron 3. Remember that what you can use to confirm iron 2 at this stage is redox reaction, heat reaction with oxygen. When it's oxidized by oxygen to give you reddish brown precipitate, which is what? Iron 3. It means that iron 2 is confirmed. Okay? Or you say iron 2, iron 3, confirmed. Iron 2, iron 3, confirmed. If in that redox reaction it gives you reddish brown, from green precipitate to reddish brown, it means iron 2, iron 3, because they obey redox reaction. Then with 2 drops of dilute NaOH solution, if it's giving you blue precipitate, suspect copper or silver. How do you differentiate it? Add 2 drops of ammonia. When you add 2 drops of ammonia and it's giving you blue precipitate, wow, still talk about copper or what? When you add 2 drops of ammonia and it's giving you blue precipitate, still talk about copper, don't talk about silver, because 2 drops of ammonia here will be giving you brown. So when you now add excess of ammonia and it's giving you deep blue solution, know that copper is confirmed. Deep blue solution, not precipitate. That means copper and zinc are very soluble in what? Ammonia. Copper and zinc are very soluble in ammonia. Aluminium, zinc and lead are very soluble in excess sodium hydroxide. I repeat, aluminium, zinc and lead are very soluble in excess sodium hydroxide, whereas copper and zinc are very soluble in excess ammonia. Please, that keyword excess must be there. Then for this silver, it forms blue precipitate like copper, but when you add 2 drops of ammonia, it gives brown precipitate. But when you now add excess ammonia, it gives colorless solution. When it gives colorless solution, that is, precipitate dissolves, no precipitate form anymore, it means silver is what? Confirmed. When it gives you from that brown precipitate, it will be sending a signal to you that silver is there. And from that brown to colorless, it means that silver is confirmed. That is the elementary level for WAEC. When you come to university level, you will now see that all these cations and more of them have their what? Groups. Group 1, Group 2, Group 3, Group 4, Group 5, Group 6, and Group 6 cations where potassium, sodium belong do not have precipitating reagent. Why? Because they are very soluble. But group 1, the precipitating reagent is dilute HCl. Group 2 is H2S in acidic form. So you now see that you will be talking about precipitating reagents for all the groups at university level or in higher university level. So what we concentrated is in WAEC standard or secondary school level. Now you have been able to note this using or determine your cation and anion using your sodium hydroxide and ammonia. Yes. And also with dilute H2SO4. We have succeeded to get or analyze your cations. Now another confirmatory test we have to use to get your what or to confirm your cations is called flame test. How do we do that? Get your test tube, fill it halfway with water. Fill it halfway with water. What you now do is get your salt, put it on a sheet of paper, add drop of conc HCl, add drop of conc HCl on it. Then use the bottom of your what test tube to what? Soak it so that the salt will wrap on the bottom of the test tube. Once you have achieved that, on your flame and put it on the flame to check if there will be color imparted to the flame. If the color imparted to the flame, if there is color imparted to the flame, it means it is positive to flame test. Now, if the color is persistent golden yellow, it means that you'll be talking about sodium ion. Then, if the color is lilac or violet, that is purple color, it means you are talking about potassium ion. Then if it is brick red, it means you are talking about calcium ion. For pale blue, if it is pale blue, it means that you are talking about lead. That means lead has a color it imparts to what? Flame. If you talk about bismuth, antimony, they also have pale. Note that also that barium will be imparting pale green. Okay, now testing for the anions, there are two possible tests you are to do for you to test your anions and confirm it. First is called dry test, whereas the second is called wet test. The first, that is called dry test, from the name dry test, it means you are using dry sample to do the testing. That is, for carbonate, you get the dry sample, small of it, and you add 0.5 cm cube of 2 molar HCl. It doesn't necessarily mean that you'll be measuring 0.5 cm cube. Just get your dry salt sample, just put few drops of 2 molar HCl inside it. Now, while you are trying to test for this carbonate, it's very important that you be very observative. You are to be observant of what will happen to the sample. As you carry that small salt sample which is dry and you are adding few drops of 2 molar HCl, check for if effervescence will occur. Now, how do we know what we call effervescence? If you want to understand what it means, buy a bottle of Sprite. When you buy a bottle of Sprite, add salt, the normal salt, the salt you use to cook at home. Add normal salt inside it. When you add normal salt inside it, the way the reaction or the result you will get, the effervescence you will get is what we call effervescence. The fumes that will come up, the fumes of the Sprite that will come up is because of what? Carbonate. That is CO2 gas. The reason why we are using the salt to put inside the Sprite to be able to see what or how effervescence look like is because CO2 gas is one of the preservative gas that is used to preserve all these carbonated drinks, Coke, Sprite, and so on. They use CO2 gas to preserve it. Okay, so when you add that salt, the reaction you will see, the fumes that you will see is what we call effervescence. So exactly how it is, that is how it will react, or that is how or what it will give you for you to know that CO2 gas is present in it, in that salt sample. So what you do, as you are adding few drops of 2 molar HCl inside the salt sample and you see effervescence, by the time you are about to pour that few drops of this, bring lime water close to it. So as the effervescence is about taking place, bring it close to the lime water bottle. That gas will enter inside that lime water because it's going up the test tube. The gas will enter inside the lime water, and what you will notice inside that lime water bottle is that it will turn it milky. It will look as if a milky substance is formed. That is because of the gas which entered inside it. Now, my advice to you students is that while making your report on salt analysis, please try in as much as possible to see that your report is in a past tense or in a reported speech. That is, colorless and odorless gas evolved. That is, we put it in a reported speech, or that is in a past tense, because you just performed it and you are now reporting it. That is what I mean. Don't put it in a present tense. Effervescence occur. Colorless and odorless gas evolve, which turns lime water milk. No, put it in a reported speech. So that means when I get my dry salt sample and I add few drops of 2 molar HCl inside it, as I'm adding it, that effervescence that will occur, as that effervescence is occurring, make sure that if this is handy, this is close by, very close by, just pick it and check out if it will turn the lime water milky. Once it turn it milky, the implication is that CO2 from CO3 2 minus is present. Sometimes once the effervescence occur on addition of HCl, drops of HCl, once effervescence occur, let you have it in your mind there is possibility that this gas is there, because some persons can be too slow. Why I'm saying it is because some students can be too slow, as they just add the few drops of 2 molar HCl inside it. Uh, then because of they are very slow, by the time they will now bring the lime water to face the top of the test tube inside the lime water to see if it will turn it milky, you will now notice that the gas have finished evolving because this happen in milliseconds. The gas that is evolving, which is CO2 gas, is evolving in milliseconds. So if one is too dull or too slow in performing this task, the implication is that there is possibility that it will not be able to notice the turning of the lime water milk. So it's only when you are fast while adding this, you bring this close immediately and check if you turn the milk that you will get actually how it turn its milk. Okay, so have it in your mind in case you are a dull type. Once you add few drops of this and effervescence occur, just note that you should be suspecting this. Don't write confirm because it is a dry test. A dry test is not often used to confirm a particular anion present. It's not always used or is not often used. The one we use to confirm presence of anion present is called wet test, and we'll still look into that. Okay, same thing goes to this. Get a dry sample, a dry salt sample, add few drops of 2 molar HCl. As you are adding it, gas will be evolving, but for you to notice that gas well, heat it, then add acidify potassium dichromate pepper. That is, bring a potassium dichromate pepper, acidify it with HCl, that touch it with HCl, then bring it close to that to the content in the test tube that you are heating. Bring it close to it on the top of the test tube. When you bring it close and it succeed to what? Turn the potassium dichromate pepper blue. That means SO2 gas from SO42 anion is present. That means when you add few drops of 2 molar HCl inside this dry salt sample, heat it, bring potassium dichromate pepper, moist it with few drops of like a drop or 2 drops of acid, like for instance HCl, just moist it with an acid, carry that pepper, get it close to the wall, top of the wall of that test tube, get it close to it. Once it turn it what? Blue, suspect this, that it will be present. Another thing is that this gas SO2 from SO4 is always having a suffocating smell. That is why while doing this experiment on anions, it is very important that you take personal safety precautions. Wear your face mask, your eye goggle, your nose cap, your lab coat, wear your hand gloves, because this gas, it can just ooze into your nose and can cause respiratory issues and can lead to death, or it can ooze into your eye and can blind your eye, so it can make you blind, and that will be another issue. So that is for SO2 from SO4. This is a dry test for it. To test for presence of chloride ions, we have tested for carbonate, we have tested for sulfate, we are now testing for chloride and for nitrate ion. That means in your salt analysis, in determination of anions, the possible anions they can ask you to test is SO4, Cl, dichloride ion, then nitrate ion, and carbonate ion. That means they are the 4 possible anions they are to ask you on your WAEC day. And possibly in first year university, there are the possible anions they can also ask you. Yes, even though there are one or two more anions they can also include, but they are the major possible anions they can ask you in your first year in the university. Okay, now we are to test for the chloride ion. Remember we said we have dry test and we have wet test, and dry test is what we use first, where we use the dry salt sample and test it with either HCl or H2SO4 as the case may be. Why I say as case may be is because when you talk about carbonate you use HCl. When you talk about sulfate you use HCl. But when you talk about chloride and nitrate you use H2SO4. Okay, now as you test it with this acid HCl H2SO4, we are checking the presence of gas being evolved or not evolved. If this gas evolve and it succeed to meet up with this criteria or this observation we wrote here, it means that gas is present. So without saying, get a small quantity of the dry salt sample. When you get it, add few drops of conc H2SO4. Please ensure you take safety precautions while doing this. Wear your hand gloves. Remember you are using conc H2SO4. You are using conc acid in this dry test. You are using conc acid. So wear your hand gloves, cover your nose, wear your face mask, your nose cap and your lab coat so as to protect yourself. Even wear your eye goggle to protect your eye, because this gas being that are to be evolved, they have tendency to blind someone, cause blind to anybody who handle it carelessly. Okay, so I have collected a small quantity of the salt sample. I've added few drops of conc H2SO4. Then as I added it, I heat it on a flame. Just heat it on a bouncing flame. As I'm heating it, to make sure or to bring out the gas well. Why I'm heating it is for it to bring out, to help in bringing out the chloride gas that will be there if it is present. So as I'm heating it, I will bring the bottle of ammonium hydroxide. I'll bring the bottle close immediately so that the gas will enter inside that bottle of ammonium hydroxide. As it enters, if it forms white dense film with ammonium hydroxide, know that chloride ion is there. That means HCl from chloride ion. So it will give you a colorless acid gas with pungent smell, fumes in air. If care is not taken, this smell can get into your body and cause something else. So you have to wear face mask as this smell is coming out so that it not harm your body. So colorless acid gas with pungent smell, fumes in air, which forms a white dense film with ammonium hydroxide. Okay, that gas, once it enter ammonium hydroxide bottle, it will form a white dense film. It means chloride ion is there. Then dry salt sample plus few drops of conc H2SO4. Again, here H2SO4, here H2SO4. Then heat it to make sure that the gas will come out well, plus copper tonics. Just take few pieces of the copper tonics and put inside. If you notice oil drops on the walls of test tube, pungent acid gas films often colored brown, then the brownish color or the brownish films deepen on addition of copper tonics. It means you're talking about nitrate. Okay, we want to embark on wet test. Remember, we have discussed the dry test approach, and we said you are using a dry salt sample. You either use ConKCl or ConK2SO4 as the case may be. We mentioned that because for sulfate and carbonate you use ConKCl, but for nitrate and chloride ion we use ConK2SO4 to get the dry test done. And also it's important to note that while reporting what you got from your dry test, it's important to know that you don't use the word confirm. Use likely suspected or likely present. Suspected or likely present. I think that's better. Don't use confirm. Yes. So that means if I write HCl from chloride ion at my inference part, at my inference part, if I write this from this, I will say this from this likely present or suspected. HNO3 from NO2 suspected or likely present. SO2 from SO4 to sus. HNO3 and NO2 from NO3 minus suspected or likely present. SO2 from this suspected or what? Likely present. So we are using these terms to write in your inference part. You don't write confirm. It's very important to know that, because dry test is not a confirmatory test. It is the wet test that you can now use and say confirm. Now, why are we preparing wet test? We want to prepare wet test so that we can test for chloride ion, nitrate ion, and sulfate ion. We want to confirm it using wet test, and even for carbonate. But for carbonate, we don't prepare sodium carbonate extract. We don't prepare sodium carbonate extract. We only prepare sodium carbonate extract of that salt when you are testing for chloride, nitrate, and sulfate ion. Why are we preparing sodium carbonate extract of that salt sample? For us to test these acidic radicals or these polyatomic anions. Why we are doing so is for us to precipitate or remove the heavy metals that will likely be present in that salt sample, because most or some of the metals we have or as cations, some of the metals or some of the cations we have while performing salt samples, some of them are heavy metals, and when those heavy metals remains there, it will interfere, it will bring an issue, it will interfere with the result of the acidic radicals we will get. It will make us not to successfully get this acidic radical very well. So for us to avoid their interference, we need to prepare sodium carbonate extract so as it will precipitate them out. Then we get a filtrate that will help us to determine the presence of these acidic radicals or the anions. How do you prepare this sodium carbonate extract? Remember I said this sodium carbonate extract we are to prepare is used for determination of chloride, nitrate, sulfate ion. We don't use it for determination of carbonate, presence of carbonate. You see, sodium carbonate. For carbonate is already a carbonate ion, so it will take care of it by itself, take care of the heavy metal by itself. But these ones are not carbonate, so we are preparing it for them to work, for this sodium carbonate to be able to take care of the heavy metals. Okay, So we now say get some quantity of sodium carbonate salt, get small quantity of the salt sample given to you, mix them with water. Let's say the quantity you collect as your sodium carbonate and the quantity of the salt sample, let them be relatively equal. Then add water to it. So I put small quantity of the salt sample, small quantity of the sodium carbonate, and I've added my water. I'll shake it well so that both of them will mix well. Then filter them with my filter paper. Once I do that, my filtrate is what we will call sodium carbonate extract of that salt sample. This is my filtrate. We call it sodium carbonate extract of that salt sample. Then once I filter it, I'll keep the test tube containing the sodium carbonate extract. I'll keep it. I will now be collecting small quantity from that test tube, small quantity into this other test tube. I'll just put few drops here. When I put few drops here, I will either put few drops of dilute HCl. I'm now trying to test for sulfate. If I put few drops of dilute HCl, that means I will know that it is barium chloride I will use. But if I put few drops of nitric acid, it means that I will be using barium nitrate in this part. Please note it. So if I put few drops of this, I will heat it small. As I put this and heat it, you'll be noticing that as it is cooling, white PPT will be about to form as you are adding few drops of barium chloride. So when you put few drops of dilute HCl, heat it, on cooling, add few drops of barium chloride. You will see a white PPT form like milk. Like you add milk to water, that is how it will look like. White PPT will be formed. Then when you add, because it's barium chloride, when you add dilute HCl in excess, what you notice is that there will be formation of white precipitate. White precipitate will be formed, and that means there will be insoluble white precipitate formed, which is an addition of excess dilute HCl. Whenever a precipitate is formed, it means that an insoluble solution is formed. Please note it. So, or whenever soluble solution is formed, it means there is no precipitate. Are you getting it? It is just two-way. So, I repeat, take few drops of few quantity of that filtrate, add few drops of dilute HCl, heat it small. On cooling, add few drops of barium chloride. Once you form a white PPT, like you added milk to water, the way it look like, that is how it will form. Then add dilute HCl in excess to check up something. Why? You are checking if that precipitate will still be what you are checking if that white precipitate form will be soluble or will be insoluble on addition of excess dilute HCl. If it is still insoluble, it means you are talking about sulfate ion confirmed. But if it gives you white precipitate soluble on addition of excess this, know that it is this brother of sulfate ion that you'll be talking about confirmed. Trisulfate 4 ion. Trisulfate 4, this one, that is what we'll be talking about. I repeat, when that white precipitate is formed on addition of few drops of barium chloride, when that white precipitate formed on addition of few drops of barium chloride becomes insoluble on addition of dilute HCl in excess. If it becomes insoluble, it means SO4 2 ion is what you confirm. But if it forms no precipitate, that is, if that white PPT just remain white, non precipitate anymore, it will give you a white solution, white soluble solution that is no precipitate in it. Please know that it is this second anion that will be confirmed. For this one, it's mostly asked for year 1 students, but sulfate, this and carbonate are asked for WAEC students. Okay, this mostly one of the anion they can include in the anion you are to detect. Bromine ion, iodine ion, and all have it. They can include it in your year 1. But for WAEC students, this are what they can ask from you. Okay, please note it. Forming insoluble white precipitate on addition of excites, this should come to your mind. Sulfate, confirm. But forming a white soluble solution, no precipitate, white soluble, that means you have to leave that test tube to stand for some seconds to check if this precipitate will be soluble or not what soluble. If it gives you an insoluble, know that it is. If it gives you a soluble white solution, no longer precipitate solution, it means it is this. Please note it. Okay, now to confirm for chloride ion, nitrate ion, and also carbonate ion, we want to confirm them. We said for the one of chloride, nitrate, and sulfate that we need prepared sodium carbonate extract, the filtrate, to do the confirmation. We talk about that. Now, also we said we don't need the sodium carbonate extract for one of what? Carbonate ion, because already it's a carbonate, you can take care of the heavy metals on their own. But the one of chloride, nitrate, and sulfate, the heavy metals interferes in determination of it, so we need to precipitate it or filter it out. So there is need to precipitate the presence of heavy metals in that salt so that we will get the result accurately. So that is why we are preparing sodium carbonate extract. That is a wet test, because when we do that, we'll be able to confirm that this is present, or this acid radical or anions is not present. Okay, yes, so that is where we go for the one of chloride. To confirm it, remember we said we are using NSN to denote our sodium carbonate extract of that salt. That does not mean that you have to write NSN is a must. No, write your own in full: sodium carbonate extract of the salt, 0.5 cm cube of sodium carbonate extract of the salt plus. Are you getting it? Now, as I said, this 0.5 cm cube is not a must that you start looking for a measuring cylinder or what have you to measure at 0.5 cm cube. What you do is just from that your filtrate, sodium carbonate extract, that's your filtrate on the test tube, pour small quantity inside what? Another test tube. When you do that, put excess dilute HNO3, that is nitric acid, put it. When you put excess of it, just put excess of it, put it with, apply caution while putting it. Just put it excess. That does not mean that you should fill it up to test tube. No, just put enough quantity of it. That is what we mean. How will you know that you have put enough quantity of it? Get litmus paper, blue litmus paper, put it inside the solution to know whether it will change it to red. If it's still keeping that moist blue litmus paper blue, it means you should add more of HNO3. But if it has turned that litmus paper red, it means you have succeeded to put excess of this. That is a technique you have to apply there to know when it is excess, so that you will not fill up the test tube just like that and waste your reagents. So when you have added excess dilute HNO3 and you have confirmed it with blue litmus paper that it is excess, heat it small, then put few drops of silver nitrate. When you put few drops of silver nitrate, when the preparation gives you white precipitate soluble in dilute ammonia, it means that this is confirmed. That means that once you put few drops of this and it's giving you white precipitate and you added ammonia, dilute ammonia inside it, and it's giving you a soluble solution, white soluble solution that is no longer a precipitate, it means that chloride ion is confirmed. That is how we say white precipitate soluble in dilute ammonia. Okay, then take small quantity of that sodium carbonate extract or that salt sample, add excess H2SO4. Remember, I say how you will know you have added excess of an acid is by using a blue litmus paper, moist it, put it inside that mixture of sodium carbonate extract and the H2SO4. Put it inside that test tube to know whether it will turn the blue litmus paper what red. If you turn it red, it means that the acid you have added is in excess. It's okay. But if it is still turning it blue, if it is still retaining its blue color, the implication is that you need to add more of this to make it be enough, or to make it to turn that blue litmus paper red. When you have succeeded that when you have noted well that you have put excess H2SO4, remember I said putting excess doesn't mean you should fill your test tube. Apply caution, apply sense while doing that. So when you have confirmed it with your blue litmus paper and it's okay, heat it small. Then as you are heating it, get your saturated ferrous ammonium sulfate. It is a salt. I think it's white in color. It's a salt. What you do is dissolve it in water. Get small quantity of it, pour water inside it, shake it and filter it. The filtrate, check the quantity of this that you have. If the quantity is, let's say, 2 cm, you don't need to measure it, just know the quantity. Then ensure that the quantity of this you are to add will be equivalent, the quantity of the filtrate of this you have, that is saturated ferrous ammonium sulfate with water mixed together, the filtrate you will have, the quantity you are to add here will be almost or equal to what the quantity of this and this you have in your test tube. When you do that, add conc H2SO4 while holding that test tube in a slant position. I'm holding the test tube in a slant position. I'll be adding conc H2SO4. So when I'm adding my conc H2SO4, if you give me a dark brown ring at the interface, if you give me a dark brown ring, it means we are talking about what? NO3 ion. So what you'll be writing is confirm, because this is the confirmatory test for it. Web test is the best test technique used to confirm any anion, because with the preparation of sodium carbonate extract, it will remove those interferences, those factors that will interfere, those heavy metals that will interfere in your result. It will get rid of them, it will remove it. So what you now write is NO3 minus 1 confirmed. Then for your carbonate, I say you don't do preparation of this because it's already carbonate ion. So it can take care of the what heavy metals that will be interfering in the result, to take care of it. So what you do is that get the salt sample itself, not the sodium carbonate extract, not the sodium carbonate extract, but the raw salt sample itself. Add equal volume of potassium dichromate solution inside it. That means if I have small salt sample, I will put small potassium dichromate inside it. When I put it, I will shake it. Okay, then add 2 molar HCl, that is hydrogen chloride. I will add small quantity of it, join, then heat it. As I'm heating it, I'll bring lime water container, a bottle containing lime water. I'll bring it close to that test tube that I've heated, or I am heating, so that the gas that will be coming out, I will check it whether it will turn the lime water milky, whether it will form milky lime water inside that lime water bottle. So once I position it and the gas enter, and if it turns that lime water bottle to milky color, it means that CO2 gas is inside it. And CO2 gas is from what? CO3 ion, that's carbonate ion. That is when you say CO2 from CO3 CO3 ions confirm. That is CO2 from carbonate ions confirm. Please note that. That means, in summary, sodium carbonate extract is used to prepare or to confirm the presence of chloride ion, nitrate ion, sulfate ion, and that is what we call wet test technique. But we don't use it to confirm carbonate. Why we use it to confirm chloride, nitrate, and sulfate ion is because they have, this sodium carbonate have ability to precipitate or remove the presence of heavy metals, or the heavy metals that will interfere in the determination of the acid radicals or the polyatomic anions, or these anions, monatomic anions. So all these anions, whether polyatomic or monoatomic, this polyatomic anion, this monoatomic anion, they are called acid radicals. If we want to confirm it and we don't want to see or to have interference of heavy metals, we prepare sodium carbonate extract so that it will get rid of those heavy metals, so that we will easily confirm it. No interference of the heavy metals. Okay, so when you are following wet test techniques, it means what you will write in your interference part, in your inference part, please, not interference. In the inference part is that this confirm, this confirm, CO2 from this confirm. You shouldn't be writing present or suspect. You are no longer suspecting, you have confirmed it. Okay, thank you so much for watching this video. Feel free to click like, click subscribe, share with your friends, and see you in our next practical class.